we will discuss the magnetic circuits. Here, I cover series magnetic circuit, parallel magnetic circuit, dot rules, series aiding magnetic circuit, series opposing magnetic circuit. Series magnetic circuit. Here, this is the magnetic core with the air gap on one of the leg, and there is a winding wound over the another leg with number of turns equal to n and carries the current I. And the MMF produced by this current is nothing but N into I, and this produces a flux in the magnetic core that is called phi, and that also flows through the air gap. And here LC is the mean core length of the magnetic core, whereas the air gap length is Lg. Permeability of the air gap is mu naught and area of the air gap is Ag. Magnetic core permeability is mu r. Area of the magnetic core is Ac. Having known these parameters, it can be represented in terms of electrical circuit like this. So it works as a source, that is Ni, MMF. This produces total flux. Here S1 is the reluctance offered by the magnetic core to the flow of the flux phi, and Sg is the reluctance offered by the air gap to the flow of flux. Using magnetic Ohm's law, flux can be calculated like this. Flux is equal to MMF, that is Ni, divided by total reluctance. Total reluctance is nothing but S1 plus Sg, so which can be represented as capital S here. Next, coming to the parallel magnetic circuit. Here, in the parallel magnetic circuit, there are totally 3 limbs on the magnetic circuit. On one limb, n number of turns are wound and which carries a current called I, and this produces total flux phi1, and this is divided into 2 parts, phi2 and phi3, that is in second leg and third leg. So the total flux can be written as phi1 is equal to phi2 plus phi3. Here, the reluctance offered by the main core, that is left hand side core, is ABFE length, and that reluctance is represented by S1, whereas the reluctance offered by the path from B to E is represented by S2, whereas the reluctance offered from B, C, D, E is represented by S3. So the total reluctance of the circuit is nothing but S1 plus S2 in parallel with S3. And it can be represented in the electrical circuit form, that is MMF Ni is in series with the main core reluctance, that is S1, whereas the other second leg, third leg reluctances are S2 and S3, and they are said to be their parallel connected reluctances. So the total flux produced by Ni is divided into phi2 and phi3. So the total flux is given by phi1 is equal to phi2 plus phi3. And coming to the total reluctance, S1 plus S2 in parallel with S3, S3 divided by S2 plus S3. This is the total reluctance of the circuit. And the total flux produced by the source MMF is nothing but phi1, which is equal to phi2 plus phi3. So the total flux can be written as phi1 is equal to total MMF divided by total reluctance. Next, dot rules. Before it is discussed, let us see what is the purpose of this dot rules. Why should we use it? The purpose of these dot rules is to find the polarity of the mutual inductance or mutual induced EMF with respect to the sign of the self-induced EMF or self-inductance. And this polarity of the mutual induced EMF or mutual inductance depends on two factors. One is called the sense of winding over the core. The other is direction of current in the winding. Dot rules can avoid the complicated diagrams like this. Here, this is the iron core or magnetic core carrying the two coils, and two coils are also carrying the current. So here current enters the coil here. Similarly, here also current enters the coil like this. For this sense of winding, applying the right hand thumb rule, flux produced by each coil current can be obtained as phi1 and phi2, and it's observed that the fluxes phi1 and phi2 are flowing in the same direction, means they are aiding each other. So drawing every time like this is very difficult. So a small winding is drawn, and at the entrance of the current entering the winding is put as dot like this. Similarly, in the other coil also, where the current enters the dot, here is also represented with the dot like this, and both can be shown like this. Similarly, for another coil, here the coil 1 with this current sense and the winding sense, phi 1 is flowing from top to bottom. Similarly, phi 2 is also flowing from top to bottom. That means they are aiding each other. Instead of drawing this circuit, it can be represented with the coils like this. So here current leaves, here also current leaves. So leaving points at the winding, we put dots here. Here current is leaving, I1 is leaving this winding, so it's put dot here. Similarly here I2 is leaving the winding at this point, so put dots here. So in both the cases, the flux phi1 and phi2 are aiding each other. Having known this simple circuit with windings and dots, so two rules are framed. They are called the dot rule 1 and the other is dot rule 2. Dot rule 1 says when current enters the dots or leaves the dots in two magnetic coupling coils, then the polarity of the mutual induced EMF or mutual inductance is same as that of the self-induced EMF or self-inductance. It can be seen here, this is the coil 1 and coil 2 and their self-inductances are L1, L2, and here the coil 1 carries the current I1. So current entering the dot here. Similarly here I2 is entering the dot here, then flows through the coil. Similarly here current leaves the dot in the first coil, whereas in the second coil current I2 leaves the dot here. So in both the cases the fluxes are aiding. So the sign of the mutual inductance when equivalent to inductance is calculated will get the same sign as that of the self-inductance, that is normally positive. Next, dot rule 2 says the current enters the dot in one coil and leaves the dot in the coil 2, then the polarity of the mutual induced EMF or mutual inductance is opposite to that of the self-induced EMF or self-inductance, that is normally minus. So that can be observed here. Here, this is the first coil, current enters the dot and then flows through the coil. Whereas in the second coil, current flows through the coil first, then enters the dot, means current leaves the dot. Similarly, in the second part, here in the first coil current leaves the dot, whereas in the second coil current enters the dot. So in both the cases, the fluxes phi1 and phi2 will oppose with each other. So the sign of the mutual inductance, when its equivalent inductance is calculated, will get the opposite sign of that of the self-inductances L1, L2. So let us understand the dot rule 1 with an example. Suppose there are two self-inductances L1 and L2 connected in series like this, and they carry current called I. Let us say dot is here, means current enters the dot in the first coil and then flows through the coil L1. Then same current will flow to the dot of the second coil, then flows through the coil L2. Same thing can be written like this also. L1, L2 are the two self-inductances connected in series like this. Current I is flowing. So in the first coil, current flows through the coil, then leaves the dot. Similarly, the current flows through the coil 2 and then leaves the dot. So in this case, current leaving the dots, whereas here current entering the dots in both the coils. So the fluxes of these two coils aid each other. So the mutual inductance for these coils will get the same sign as that of the self-inductances while calculating the total inductance of this circuit. Suppose the mutual inductance between L1 and L2 is M12 and the mutual inductance between L2 and L1 is M21, then it can be drawn in series with L1, L2 like this, M12 plus M21. Then the total inductance can be written as L equivalent is equal to L1 plus L2 plus M12 plus M21. Because both the coils carries the same current, it can be observed that M12 is equal to M21 and which can be equated to capital M. Since in this case it follows the dot rule 1, the fluxes aid each other, so the sign of the mutual inductance is positive, so here M12, M21 getting plus plus, and because both have the same value and which is equal to M, so it can be replaced here M and here also M, so the total inductance will become L1 plus L2 plus 2M. This clearly explains how the dot rule 1 works for the magnetic circuits. Let me explain how the dot rule 2 works for the magnetic circuits. So let us say here L1, L2 are two inductors connected in series. Here I is flowing through the coil L1 and L2, that is I is entering the dot of L1 first, that is current enters the dot first in the coil 1 and then flows through the coil 1, then flows through the coil 2, then enters the dot in the coil 2. That means here the two fluxes produced by the L1 and L2 will oppose each other. Similarly here, in the first coil, current flows through the coil 1, then flows through or leaves the dot, whereas in the second coil, current enters the dot and then flows through the coil 2. So here also the two fluxes will oppose each other. So this can be drawn with an equivalent circuit like this. L1 plus L1 and L2, M12, M21 all are in series. When the total inductance is calculated, it can be written like this: L1 plus L2 minus M12 minus M21. Because the flux in this case they are opposing, In both the cases, they are opposing. So the sign of this will get negative sign. That is because the self-inductance have the positive sign, automatically the mutual inductance will get the negative sign. Similarly, M21 will also get the opposite sign to that of the L2, that is minus. Since M12 and M21 are one and the same, and let us say equal to M, so substituting this M here, then L equivalent for this dot rule circuit is nothing but L1 plus L2 minus 2M. Let me summarize once. We have seen here what is series magnetic circuit, how the flux flows, what is the reluctance, what is MMF. Similarly, in the parallel circuit, parallel magnetic circuit, we have seen what is the total MMF, what is the total reluctance, what is total flux produced, how the flux is distributed among the parallel branches of the magnetic circuit. We have seen what is the importance of the dot rules and why we should use the dot rules. We have seen dot rule 1 and dot rule 2. Similarly, we have seen to explain the dot rule 1, series aiding circuit is taken into account. Similarly, to explain dot rule 2, series opposing magnetic circuits is taken and explained.